Hello, this is Sahika Genc. I'm a principal applied scientist in Amazon. Today I'm going to be talking about deep reinforcement learning for autonomous driving with AWS DeepRacer. AWS DeepRacer is a 1/18 scale robocar. We started out by thinking what could be a fun way to help people teach reinforcement learning and learn also about deep reinforcement learning. We came up with this idea about having a robocar at scale where you can train a simulated version of this car in AWS Cloud Services using SageMaker and RoboMaker, which is our cloud simulation environment, SageMaker, our machine learning environment. And then also see how your trained model performs in real world by copying your reinforcement learning model into your car and racing on an actual track. We started out as, well, this is a toy problem, but then we quickly learned it's toy cars, but not a toy problem. So today I'm going to be talking to you a little bit about things that we had learned and research we were able to conduct extend on how you can apply deep reinforcement learning to autonomous driving, and also extend and learn about transfer learning and Markov games. We launched AWS DeepRacer, an exciting way for developers to get hands-on experience with reinforcement learning in 2019. We initially previewed it in 2018 at reInvent, and it was a big success. After our launch, at the end of our launch, we had 30,000 participants. With AWS DeepRacer service, we had a simulation environment where a car can drive on a track. We allowed the racers to design a reward function which is then trained in cloud using very popular reinforcement learning algorithms. And the resulting neural network then can be copied literally through a USB drive into the car. And now you can see how your model performs in real world. We had hundreds of in-person races across multiple countries. In 2020, we increased our offering of sensors from a single camera to multiple cameras and a LiDAR. And this allowed us to enable the developers to learn about sensor fusion and how you can include sensors and multiple inputs in your reinforcement learning model. We extended our simulation environment accordingly. However, we weren't able to hold in-person races. We started an underground racing, where we had few folks set up their basement with a deep racer track and hit cars and allowed others to race on their basement track, which we call DeepRacer Underground, by sending their models that trade in the cloud. And our developers had picked this, and we grew into many participants in 2020, despite not being able to hold in-person races. In 2021, our platform grew, and we reached the 80,000 participants. We enabled virtual community races, and we also held a competition as part of AI Driving Olympics at NeurIPS in collaboration with AI Crowd, where now you can go beyond and have a jailbreak experience from the AWS Cloud Service and be able to train and extend your models beyond the popular reinforcement learning and simulation environments that we offer. We're proud to sponsor developers, and if you would like to learn a little more about DeepRacer but are not familiar with cloud services as much, I recommend you check out AI Crowd's website, and you can get the starter kit even though the competition is over. Also this year, we started enabling a student league for AWS DeepRacer. I strongly encourage you. We have scholarships, grand prize, and plus a trip to reInvent. So if you haven't had participated yet, you still have a chance. Please go and check it out. Reinforcement learning in autonomous driving has not been as popular. However, it has been a relatively good way for us to learn reinforcement learning in a relatively safe setting but still able to test your models in a real world in a safe environment. Though I must say that sometimes we turn the wheel so fast and hit some burns on the track. So we start out our reinforcement learning by gathering rewards in an episode. So we have a simulation environment, and the simulation environment is such that we have basic physics between the actual world and the simulation environment really close to each other. And the car is trained in a gazebo simulator in a Amazon RoboMaker. And in this simulation, we give rewards to the car, and rewards are something can be designed. And based on these rewards, we collect episodes, and we use a clipped PPO, policy optimization, proximate policy optimization method, to learn from these rewards how to drive on a specific track. The way the clipped proximate policy optimization works, you can find many papers, but it is based on calculating a gradient of the estimated cumulative reward using neural networks, or you can use other kinds of modeling techniques as well. In this case, for AWS DeepRacer, we're using a relatively vanilla policy gradient method, and we update a neural network, which is a convolutional neural network for single camera, and a two-headed neural network for LiDAR plus multiple cameras. And we update the policy using gradient, ascend or descend, depending on your reward function. And we continue in this feedback loop that we continue to collect episodes. We provide we have these replay buffers, and from that we learn how to drive. When we first enabled AWS DeepRacer, what we thought was that we would like to bring a human aspect to it, because the rest we can automate if you're familiar with reinforcement learning. We have the models that can be trained, relatively straightforward models that came out over the last 5 to 10 years, the code available, and they're pretty efficient. The human aspect of it was, be careful what you wish for, you may just get it, is a reward function. So throughout, when we first get started, we enabled everyone to bring their own reward function, and also personalize the action space for coarse or granular steering. So thousands and tens of thousands of models had been trained, deep neural network models, using various different reward functions. You can actually search for AWS DeepRacer reward function, and you will find some heated discussions on winning reward functions and so forth. This enabled us to learn a little bit about what the customers are doing and how they're approaching, or participants approaching to this problem. So the AGES neural network approximates the future cumulative rewards and select an optimal function. What we learned is, depending on the reward function, some people were able to get high converge their models really fast. Some of them did not converge as fast. So we started learning from the people trying different reward functions on how long it takes for these reward functions to converge. And we started seeing these patterns about, if you have a very simple reward model, and I'm saying linear in the sense that if this do that, if this do that, but in reality that it is more non-linear in the sense that it is that if you're off the track, get this reward, if you're on the track, get this reward. So it has a jump in it. And on the other hand, advanced linear functions, where people were really engineering the reward functions, that we were seeing different kinds of convergence. So we realized that there are really correlations between the reward functions and neural networks that approximates them, and how soon you can converge. So if you go to the AWS DeepRacer service today, you can get a relatively good model within an hour. You don't have to wait several days for your deep reinforcement learning model to converge. Although the model is a relatively deep model, although it is not as deep as a ResNet model, for example. So this led us to start thinking about what are other things that we can look into. We noticed this real a correlation between the neural network and the reward function. And for some of our participants, it was really taking longer for their models to converge. Some others, it wasn't taking as long. So we started looking into how can we democratize and come up with neural network architectures that could enable us and learn from different reward functions without having to train longer if we want to go deeper. So what I'm going to talk in the rest of the presentation is how learning and interacting with the customer, with the participants, and seeing that how different, even though we only enabled initially that you bring your own reward function and we'll give you the algorithm, we'll give you the simulator, it led into so many different research ideas and things that we could do for our participants in terms of reducing the latency, enabling better sim to real transfer, and also reducing the time it takes for them for the models to learn. So our first thinking was along these lines that, oh, all these reward functions, and depending on the neural network, their convergence rates are different and their performance are different. So can we find a way to democratize it? So we started working on this zero-shot reinforcement learning. Again, that AWS DeepRacer currently today is also zero-shot. There's no learning in the real world from the car. You learn only in the simulation environment. Simulation environment has one-to-one correspondence, including friction for seamless sim to real. But what we learned is that if we incorporate a deep attention layer into our convolutional neural network, we actually get better convergence across multiple reward functions and also better performance. So we started testing these models and looking at our results using GradCam analysis, which is what I'm sharing today. You're welcome to look at the paper on the details of how actually deep attention convolutional neural network corresponds to visual servoing, which was which was the method that has been used 10 years ago or so. And you can see a theoretical analysis of comparing and comparing and analyzing how convergence and stability with visual servoing is equivalent to doing the same with deep attention networks. So practically what we see here is that depending on your reward function, you see that the car will be, if the car is paying attention, it will mark those areas as hot spots and it will stay away from those areas. And as you can see that with different reward functions, we collect that warmer colors are where the car prefers to go. And in the left column here, we have typical convolutional neural networks, multiple layers. On the right-hand side, that you could see that we have the deep attention neural networks, and you can see from the GradCam that it is more pointed and focused in terms of where the cars don't want to go. So in this case, in the left column, you can see lots of hotspots that this is areas that the car will probably have to decide between these two. Uh, we want the car to stay on this track and not go out. In the deep attention network that you are seeing that those spots are fewer and we are more likely spots for the car to move forward, go straight in this case, and potentially cut the curve, which is what we expect in racing. Similarly, if I compare the left column to right column in the top images, we see that more condensed spots of hot colors, which is indicating the deep attention network is identifying areas of interest or disinterest better than the convolutional neural network. Despite that this needs further improvement, you can see that between the convolutional and deep attention convolutional, the difference is pretty stark. And we had done further tests using different kinds of environments. I'm going to share this video where the car is running with different lights. And this is with the deep attention network. As you can see that the car is not impacted by color changes or spotlights that we dropped. So in this case, we were training the car with the spotlights using deep attention networks. We had also tested some of different kinds of environments. The track changes, the friction changes a little bit, but the car using the deep attention network actually is able to align well and can change from one track to another track seamlessly. As you can see, this is actually part of a NeurIPS competition we held in 2019, again as part of IDO, which was at a much smaller scale. And you can see that the car in this case also can avoid different textures using different kinds of neural networks. Then this led us to start thinking about what if we have multiple cars and what if we have objects? So in this case, we started thinking about, well, because this is racing, the uncertainty is really high in terms of what the other racers are going to be doing. So it is not as clear as regular traffic in some sense that there are rules to be followed. In this case, the fastest racer will win, although there are a few rules that the goal is to go as fast as you can, and the people who are racing, or the models in this case, who are racing, can take aggressive maneuvers. So we started approaching this problem using a robust Markov games. So in this case, what we're trying to do is we have an uncertainty and we need to make a decision by an implicit player, nature. So we treat everyone outside of your own as the nature who is trying to play against you. And by selecting the worst case model data at every state. Now, luckily, there is a equilibrium, Nash equilibrium. Markov perfect Nash equilibrium exists for this solution. So if you follow the directions that we defined with the uncertainty you're racing against, and you can define a joint policy, which is robust, Markov perfect, Nash equilibrium. Now, even though we're able to describe the existence and we can prove the existence of Nash equilibrium, in the case of the car racing against nature, again, nature may nature may corresponds to, it could be another car racing, multiple cars racing, and or it can be a stationary obstacle. Now, we proved that we can achieve a robust Markov perfect Nash equilibrium. However, the existence relies on relatively many assumptions that does not necessarily hold in real world. Hence, we started working on various versions of utilizing how can we still design an algorithm that is relatively robust. So we came up with two algorithms. One is based on the value iteration and other is based on Actor-Critic. And we got relatively good results using Actor-Critic, and we compared it to the current state of the art at the time, which I'm going to share the results. If you go to our paper, you will see the existence. Because there's Nash equilibrium, it doesn't mean that you can actually find a solution. However, we provided our code available as this paper was published in NeurIPS, and we got relatively good results with Actor-Critic although we had defined how such an algorithm will look with value iteration. So here is a simulation environment with our multi-agent RL racing. So in this case, you can actually see this is our car racing against other cars, and you can see its LiDAR and its camera in this setting. And one thing that we also learned is that we don't really have to come up with a different algorithm for getting depth from stereo camera. we found out that if you put the images as RGB channels and use a grayscale, you can actually recover depth information quite well with multiple cameras without having to rely on heuristics. And this is an actual world. It's reInvent. Twe- And you can also have a look at an extensive, comprehensive results. So we compared our robust Marl algorithm, which is MAD-DPG based on the Actor-Critic, to the current state of art at the time, which was M3D-DPG and MAD-DPG. And in many cases, in many scenarios, this was compared with respect to the particle environment that MAD-DPG paper had utilized. We wanted to compare our algorithms one-to-one. Hence, we tested on the particle environment with different kinds of experiments where you do cooperative and also um, competitive games. And you can see videos, and we have a blog post also on the paper. In addition to the paper, you can watch the videos and see how it actually performs slightly better than MAD-DPG and M3D-DPG in cases, and significantly better in some other cases, achieving rewards. And as you can see in this plot that we increase the noise from top to bottom, you'll see more and more noise coming in. Our algorithm is in green, able to achieve higher rewards as the uncertainty increases compared to MAD-DPG and M3D-DPG, which is especially critical in racing environments since the other car can do aggressive maneuvers for competitive purposes. And our next topic, this is going to be the last topic I'm going to discuss today, was that several of our participants, they were actually training their algorithms on different tracks. So during different competitions at different countries, we also launch different tracks that people can race on. So if you go to the AWS service, you can AWS DeepRacer service, you are able to you're able to race on multiple tracks, ranging from Tokyo to London and Spain and so forth. Um, so our participants were asking us, well, what if that I use this model that I trained on Tokyo track and I tried it on the London track? Is it gonna work? And also I spent this much time and money on training, and this model is relatively good, but I want to make some improvements on it. Can I do a warm start? So this led us to thinking about, well, you can do a warm start, and our service currently enables that. But is there more that we can investigate and help our customers reduce their compute time as well as dollar amount to get to new models if they've been doing this for some time? So in this case, what we started was looking at what happens in on-policy representation transfer. And as you can see that there has been several papers that came out on this topic, which is kickstarting or allowing a start student network and exploit access to the expert teachers. And the objective here is to use a cross entropy so that you can regularize with respect to a teacher policy. And the objective again is the iteration, that you have the representation learning is going to regularize with the vanishing um, component with respect to the auxiliary policy. In the offline or in the off policy instance transfer is this very similar to policy distillation. And the idea is you select good samples. So instead of trying to regularize your model, you try to do something with the replay buffer, and you try to select good samples and find and utilize the high advantage estimates. So you're doing some kind of filtering on your replay buffer. And this, we found out, also enables relatively good models. So we decided how can we combine both, and we came up with this model called REPAINT. And in this case, we created an advantage threshold. So what happens is you collect trajectories following a teacher policy when you're training the student policy, and you compute the rewards with the current reward function, and then you have the advantage estimates. So in our case, we flipped it and we said that we're gonna follow the teacher policy and the student policy, and we're gonna alternate. And the students is going to learn from the teacher policies samples in addition to its model. When learning from the samples, we're going to put a threshold, and we're going to look at, we're going to get the samples from the student, and we're going to look at how the teacher evaluates them, and we're going to create the teacher advantages, and then from there on decide that, oh, these are the actions that I took, the teacher thinks I did well, so I'm going to start picking those and learning a model, and then in the next iteration I'm going to apply my model learning to see if I improved upon the teacher. So this is basically the repaint algorithm that we had published our results at ICML. We also published the theoretical results on convergence using off-policy actor-critic methods, that this transfer learning model actually converges, even though that it is iterating between two different on-policy and off-policy techniques in order to first transfer the representation of the neural network model using a regularizer, and then transfer the experiences using the evaluations or advantages from teacher. And here is a set of results that we have. Actually, we learned that we are really good at playing StarCraft too. We also had tested on different simulation environments. We used Mujoko to test these, and as you can see in the repaint, that we also tested with different teacher types, that we use tasks that are similar, different, or subtasks, and you can see a comprehensive result. And you can see that our initial goal was to reduce the training time without reducing the rewards. And we did that relatively well for Reacher, and not so well with the single card, because the problem is relatively straightforward and the tasks are different. And in the multi-car, we actually went back and forth, and we looked into the cases where you start with a teacher policy that has only no cars, and you learn to race. And then in the next objective, you learn to race with the objects that are stationary. And then we extended to learn to race the objects moving in aggressive in their maneuvers. And then in the StarCraft, we used really different. We first started using subtasks that are improved, and you can see it does relatively well, that there is a strong correlation for StarCraft in terms of the teacher and student task, and we were able to get a relatively good correlation. We also have a blog on this, and you can watch the videos for StarCraft as well as DeepRacer. I would like to complete my talk with resources. Again, as I mentioned, there's an AWS DeepRacer Student League. I hope you'll be able to join that and have fun. If you are more interested in just learning about it, but are not into competitive environment, don't want to submit models, then there are really good resources on GitHub, free videos. Some of them are coming from AWS, and there's a big outside community as well, creating lots of resources for DeepRacer. So I'll strongly encourage